Hello geometry students, welcome to the lesson for 9.2. It can be found on those pages right there. And oh yeah, we are dealing with the Pythagorean theorem today, and also talking about what a Pythagorean triple is. So make sure you're using those extra examples. If you need some extra help, take a look there. They've got a lot of extra good examples to look at there. So first of all, what is the Pythagorean theorem? You may know already, you may not. You ask somebody, random person on the street, hey, random person on the street, what's the Pythagorean theorem? They probably will be able to tell you, even if they forgot everything else from their math class. Maybe probably is a little strong of a word, but they hopefully could be able to tell you. Pythagorean theorem says this: in a right triangle, and that has to be true, it has to be a right triangle. It doesn't work if it's not a right triangle. It has to have a 90-degree angle in there. You ask somebody what's the Pythagorean theorem, often they'll be able to tell you, even if they have since forgotten other things from their geometry class. They'll be able to tell you a squared plus b squared equals c squared. And you might ask them, oh, okay, great. What does a and b stand for? When do you use this? And they'll say, I don't, And then you tell them, okay, leg squared plus leg squared equals hypotenuse squared. Oh yeah, that's what that dealt with. That's right. So that's what the Pythagorean theorem says. Most people will say it like this if you ask them, but I want you to remember it like this. I want you to actually know what A, B, and C stand for. If you remember this, great, but you got to know what they stand for. So you got to know that leg squared plus leg squared equals hypotenuse squared. And so next, let's actually do a proof of the Pythagorean theorem. Some theorems we kind of just take for granted that other people have proved them. But the Pythagorean theorem, it's so important, it's so vital, and just central to much of what we do in geometry that I think it's important that we actually see one way how we can prove it. So this is one proof of the Pythagorean theorem. How many proofs are there, you may ask? Well, that's a question we'll talk about after we prove the Pythagorean theorem in this way. This is just one way to prove the Pythagorean theorem. So let's show you how this is done. So I'm going to make a square. I want you to do the same thing. Make it pretty big. And then we're going to make another square, a smaller square, within the square, but not like I'm drawing it here. Don't draw it like I'm drawing it here. I'm going to rotate this in just a second. So you're going to take this, just wait for a second until I get this rotated correctly, and I need to make mine just a little bit bigger. Expand mine out just a little bit more, and then move it into place just about where I want it. Still going to make it a little bit bigger here. Okay, so I want to make it so that it just touches the sides of the square there. So to me, that looks pretty good. So why don't you draw a picture that looks like this on your notes. So you have a square within a square, something like that. You need to pause, go ahead and do that. I'm going to move on here though and show you what the right angles are. So these are right angles right here, right here. It's a right angle right here. These are two squares, so all the corners are going to be right angles in this picture. And then we're going to call the legs of these right triangles, just like you would expect. We're going to call them A and B. So here's A, here's B. We've got another A and B here. Got that going on 4 different times here. So here's A and B again, and here's an A and a B. I could have flip-flopped the A and the B here, but I just went with A being the smaller leg and B being the longer leg. C is representing the hypotenuse. So the hypotenuse, remember, always across from that right angle. So you have a right angle here. The hypotenuse is the longest side. So this is one way to prove the Pythagorean theorem. You might look at that and say, I have no idea what you're talking about. We're getting into it here. So this is the start of this. Leave some space up here. We're going to write some stuff up here to begin, but let's see if you see what I see. What's the area of any square? Well, it's side squared. So it's side times side. So here I see the side is A plus b. The length of this whole side from here to here is a plus b. And I have a plus b times, well, the length and the width are both the same in a square, and so it's times itself, times a plus b. So in other words, you could say a plus b squared. This should equal, I don't want to put equals yet, sorry. If I take this minus the 4 triangles here, so if I take the area of the big square and I subtract the area of these 4 triangles, what am I left over with? I'm left over with this c squared part, so it's c times c right there. So I would say minus 4 times, then you have to remember what's the area of a triangle. A triangle is just half of a rectangle, so like this, half of a rectangle, so minus 1/2 base times height. The base and the height of the triangle here are a and b, so minus 4 times 1/2 base times height. So minus 4 of the triangles would equal the smaller square inside the bigger square, would equal c squared. So I want you to take out a different color at this point. Let's do this in a different color. Label these. This right here was the area of the big square. And then this right here, the 4 times 1/2 AB, this is the area of the 4 triangles. So we're subtracting that from the big square, and what we're left over with is the area of the small square. So moving on from there, another way to write a plus b squared is a plus b times a plus b. You should remember that from our algebra class, hopefully. And we also have 4 times 1/2. What's 4 times 1/2? That's 2. So we have minus 2ab equals c squared. Now, if you remember something called foiling, you can think of that. So I'm going to write that right here. We're going to FOIL, and let me write that in a different color so it stands out. So please do the same. Let's write FOIL in a different color. That's not part of the equation, so putting that in a different color helps us just show that a little nicer, a little easier. We've got first. The FOIL stands for first, outside or outer, inside or inner, and last. So first you have a squared, a times a. Outer is a times b. These are both positive, so it's going to be a plus ab. Inner, b times a, which is the same thing as a times b, so another ab. And last you have b times b. They're both positive. We have positive b squared. So we FOILed this, and we get this down here. You still have the minus 2ab that got carried down. This equals c squared. And so we can combine like terms. At this step, a light bulb may go on. I'm not exactly sure yet. If your light bulb just went on, the light bulb inside your head, but you look at that and you say, oh, wait a minute. Maybe now you see what I mean. Here's a positive 2ab. Here's a negative 2ab. What are they going to do to each other? They're going to cancel each other out. What are you left with? Bada boom, bada bing. A squared plus b squared equals c squared. The two legs, sum of the two legs squared equals the hypotenuse squared. So this finishes up the Pythagorean theorem. So this is one proof of the Pythagorean theorem. That, I think, honestly, is quite amazing. That is not, if you really think it through, not something that intuitively you would just look at a right triangle and say, oh, this side squared plus this side squared clearly equals this side squared. If we add these two together, the sum of the squares equals the hypotenuse squared. Now, like, just thinking about it intuitively, that doesn't come to mind. But this always works out. Any right triangle, pretty sweet. That actually works out. So this book right here is a collection of what somebody felt like was enough distinct proofs to come up with a book. 367 distinct proofs. You don't have to write that down, but 367 proofs of the Pythagorean theorem in this book. That's pretty crazy. And then this is the 20th President of our United States of America, James A. Garfield. Why do I put him here? He actually came up with his own distinct proof of the Pythagorean Theorem. So he's pretty famous for that in the mathematics community, that one of our presidents actually came up with a distinct proof of the Pythagorean Theorem. So just for fun here, real quick, this is from Dr. Math, somebody named Coco. Hello, Glenn Coco. Coco wondering if you knew the exact number of proofs of the Pythagorean Theorem in existence. So Dr. Math talked about a bunch of different things here, but led me to this book, the Pythagorean Proposition. If you want to buy this book, it looks like it's only the cheapest one. Somebody was selling it for, I gotta click on that here, 7 used ones, because the book was printed in 1968. It was reprinted in 1968 actually. Cheapest one with shipping, only $149.98. If you want to get those are good copies. If you want to get a like new copy, or somebody here that's selling it for a ridiculous price and will never get that, $444.84 for a like new copy, and $752. Is that all for this book? I don't know if you plan on buying that anytime soon, but it's there. Hey, it's there if you want to purchase that book. Go ahead and spend away. So let's come up now with an example. So you've done the Pythagorean Theorem before if you've made it to this point in geometry. So this hopefully is a good review problem for you, something you should already know how to do. But make a triangle that looks similar to what you see there. We're going to put some labels here in the triangle. This is going to be my right angle. My hypotenuse I'm going to call x. I don't know what it is. And then this, I'm going to say this is 5 inches over here, and that this is 12 inches right there. So solving for x, what does x equal? Use our Pythagorean Theorem. It's leg squared plus leg squared equals hypotenuse squared. So I'm going to write it like that first. Please write it like that to start. Later on you can leave this part out, but I want to emphasize that you're always plugging in the legs here and here. Even if x is the missing part over here, then you're plugging in 5 squared plus x squared would equal whatever this is squared. But x is the hypotenuse here. X is the missing part for the hypotenuse. So we have 5 squared plus 12 squared equals x squared. That's a common mistake I see quite often. Students will just look at wherever the variable is and just automatically plug it in for the hypotenuse. Don't do that. Be careful to put it where it belongs. So this belongs here because it's the hypotenuse is the missing part. But this, as we simplify this, we'll get 25 plus 144 equals x squared. This is 169 equals x squared. You take the square root of both sides, and you end up getting, what's the square root of 169? If you say 13, you're exactly right. So this squared and square root cancel. You go up to 13 equals x. Now this is 13 what? This is 13 inches. Don't forget to include those units for me. So this happens to be something called a Pythagorean triple. You see 5, 12, and 13 all as whole numbers. Does it always work out like that? No, actually it's quite rare that it works out like that in the real world. But we're going to write down some examples of Pythagorean triples. So just needed to insert a blank page real quick there. What is a Pythagorean triple? That's the other vocab word from this lesson. So Pythagorean triple, let's define what that is. It is a set of 3 whole numbers. They have to be whole numbers, so I'll underline that. Set of 3 whole numbers that, in layman's terms and in kind of more loose, less formal terminology, that I would say that actually works in the Pythagorean theorem. So your book defines it more technically. I like the technical definition, but I think this is how it will make sense to more of you. So Pythagorean triple in the book says, Pythagorean triple is a set of 3 positive integers a, b, and c that satisfy the equation a squared plus b squared equals c squared. So that's what the book says. That's true. it satisfies our Pythagorean theorem, in other words, and they're whole numbers. So it's 3 whole numbers that actually work when you plug them in. So some common Pythagorean triples. Let's write down a few common ones. Some common Pythagorean triples are what you see down here. What you will see down here. Some common ones are, we had our first one there, 5, 12, and 13. That's a pretty common one. Another common one was 3, or is 3, 4, and 5. You see those 3 going together a lot. I feel like I should flip-flop those. So I'm going to put this one up here just because that one is kind of the first one. So there we go. Flip-flop those 3, 4, and 5, 5, 12, and 13. The next most common one, 7, 24, and 25. Those go together. Another common one with the lowest integer going in order. So 7, 24, 25, 8, 15, 17, 9, 40, and 41 is a Pythagorean triple. And 20, 21, and 29. Are there more? There sure are. And if you want to see what some of those other ones are, you could try different numbers yourself, or you could go to a source like Wikipedia here, which has a pretty good say, or pretty good base of knowledge about Pythagorean triples. So here's a bunch more. If you're interested, you can look at this yourself. But we got a ton of other Pythagorean triples here from 0 to 100, and we got even more there. So there's way more than you ever probably need to know for what you're doing here. But Pythagorean triples, you got a whole smattering, a whole list of them right there as well. But for our purposes, this is all we really need to know. So I'll circle that, and these are some common ones. Basically any set of 3 whole numbers where you plug it into the Pythagorean theorem, the 2 smallest ones added together squared. So the 3 squared plus 4 squared equals 5 squared. 5 squared plus 12 squared equals 13 squared. 7 squared plus 24 squared equals 25 squared, and so on. It works for all Pythagorean triples like that. And let's try a final example here. We're going to find the area of this triangle that we're about to draw. So I want you to get out something to draw some straight lines with here, and let's draw what, as best we can, is an isosceles triangle. So this right here, that looks pretty good to me. I think I'm going to adjust that just a little bit. Okay, so I like that a little better, and then put a straight line down here for me as well, and we're going to look at this one in particular. So take out a different color just to make this stand out. I'll put this in my different color here. We're going to look at this one specifically first. So just kind of outlining the one I drew right there. And being the perfectionist I am, I just wanted to make that look a little clearer, so that black line staying outside there. I wanted to find the area of this whole big isosceles triangle, but to do that I'm going to need to find the area of one of these triangles first. So let's put the right angle measure here. I know that's got to be true, and let's also say that these two are the same. Alright, and then these two are also going to be the same. So this one right here and this one right here, I'm going to say this is 25 m standing for meters. Same thing over here then, 25 meters. This is 10 meters, and this is also going to be 10 meters then. And so what we're trying to do here is, let's write this down up here, find the area of the, we'll say the large triangle in this picture. So find the area of the large triangle, the big outside one. What is the area of that triangle? So how could we figure this out? Well, we would have to know that the area of any triangle is 1/2 base times height. So here I have the base is 10 plus 10, that's going to be 20. But the height, I don't know that yet. I do know that the kind of the height on a slant is 25, but I want the height perpendicular to the base. I need what that is. I don't know what it is yet, so I'm going to call it, why don't I just go with h for height. You could call it x if you wanted to later on, but we'll go with h here. So what's the theorem say? What's the Pythagorean theorem say? It doesn't say that leg squared plus hypotenuse squared equals leg squared. It says leg squared plus leg squared equals hypotenuse squared. So in this case, I need to say 10 squared plus h squared equals 25 squared. So see the distinction here. So this time a leg is missing. Over here in example 1, the hypotenuse was missing. So make sure you keep that straight. If you remember leg squared plus leg squared equals hypotenuse squared, that makes remembering that very, very easy. So this one, we get this in our next step. 25 squared is 625. From there, if you subtract 100 from both sides, you're getting closer to what you need then. You have h squared equals 525. And then from there, we can take the square root of both sides, and I get h equals, well, what's the square root of 525? So you can either plug this into a calculator. If they say that it can be approximated, then you could plug it into a calculator. But let's say they didn't say that. So off to the side here, let's put the list of, let's use a different color for this too. So a list of perfect squares. The other way to do this is the factor tree way. But the list of perfect squares, once you get the hang of this I think is faster, it's easier than the factor tree way. So the list of perfect squares, what are they? What's 1 squared? It's 1. We don't need to use that one though, because that doesn't help us break this down any farther. 2 squared though is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. So on. We get 36, 49, 64, 81, 100, 121, 144, 169, and so on. So this list would continue. This is mostly what we need though. So we just need to check this list of perfect squares. So let me show you how I would go about doing this with a calculator. So if you weren't sure what the biggest number in this list was that went into here, just try different numbers. So 525, I know any of the even ones won't go into there because that's an odd number to start. So I could try 9, see if 9 goes into there. So divided by 9, that does not work. So it's not a whole number there. Let's try 525. I bet you would have already seen that 525 would divide by 25, excuse me, and we get 21. So from there, I notice that I can't break 21 down any further. There's no more perfect squares that go into there. So at that point, knowing what I know, I am pretty sure actually that I know for sure that 25 is the biggest one that goes into there. Let's say that wasn't clear to us though, so we could keep trying. 525 divided by 49. You notice that doesn't work, and now we're getting too low. 49. If I do more than that, I'm going to get a number that I've already checked. So I've already checked 9. If I go less than 49, more than 49, I'm going to have a number divided by 81. That let's just do that to make sense of what I'm saying there. You get 6.48, which I've already checked 9. If 6.48 doesn't go into there, if 9 doesn't go into there, 6.48 doesn't go into there either. That's not going to work. It's just getting too big at that point to have anything else that's going to work. So 25 is the one that actually works here in this list. So we have 25 times, it was 25 times 21. So what can I do with the 25? This part, remember you can break this down. It's like the square root of 25 times the square root of 21. Square root of 25, I can take out the 25 as a 5. So this can be written like this instead. The 21, that's still under the square root. So if you were to say what's the height you could say is either this as an exact number, 5 times the square root of 21 meters, or if you were to plug this into a calculator, let's do that at this point. If they let you take the square root right away, or they didn't ask you for the exact answer, I should say, in simplified radical form, we could just take the square root of 525 right away, and we would end up getting, where's my square root button? There it is. That's the cube root button there. Over here, there we go. So the square root of 525, 22.91, if you round that to two decimal places, to 2 digits, to the nearest hundredth. But just to show you that that's the same as 5 times the square root of 21, we have 5 times, and if we hit 21 square root, that would take the square root of 21, multiply those together, there it is, 22.91. 22.91, and then the 2, that's 4 or lower, so we round it down there. So this would be an important step, but not the final step. We found the height. We need the height now in our area of a triangle equation. So the area of the original triangle, the A stands for area, so the area of the, rather than say original, I'll say the large triangle, because that's what I said up here. So the area of the large triangle is 1/2 base times height. What's the height? That's getting plugged in right here. We just found out what that was. What's the base? The base was 10 plus 10, which is 20. So we're going to plug in 20. The height is 5 radical 21. I'll leave that as an exact number for right now, because that will give me a better answer here in the end. If I need it as an exact answer, I would have to have it like this. So what's half of 20? Half of 20 is 10, and 10 times 5 is 50. So you have 50 times radical 21. You would have this many meters squared, because it's an area. It's meters here times another meter measurement here. So it's meters times meters, giving you meters squared. You can say this, which is approximately, we'll take out our calculator here and type that in. So 50 times square root of 21 gives you about 229.13 if we round that off to 2 decimal places. So 229.13 meters squared. So let's box that in. It's our final answer. And hopefully you understand the Pythagorean theorem either a little better than you did before, or you just got a good review there that refreshed your memory on how to use the Pythagorean theorem.